Hello and welcome to yet another video of Cornerstones of Math. Today I am going to analyze one particular hypothetical situation using famous probability theory. The context of the main problem is as follows. A highly infectious disease transmitted by virus is spreading across the country and threatening the public health. Luckily, the vaccine was swiftly developed and people started getting vaccinated. However, there's this dude who hasn't learned the conditional probability during his school years, claiming that the vaccination is practically ineffective. His argument is as follows. Currently in this country, 1,000 people are hospitalized for getting infected by the virus and showing the symptoms of this disease. Out of these 1,000 patients, 400 people have been vaccinated, and the remaining 600 people are who haven't been vaccinated. Our dude is claiming that since 40% of the hospitalized patients are the ones who already had been vaccinated, these vaccines are simply not effective enough. Now, deciding whether a certain vaccine is effective or not is a subjective judgment, so there's nothing wrong about him making such judgment. The real problem is, he's making that judgment based on wrong probability. More specifically, he is using wrong conditional probability. So let us think about what would be the more suitable probabilities to assess the situation and then calculate those probabilities. In order to do that, we need the population status of our hypothetical country. Suppose that this country has a total population of 10 million, and among them 7 million people are vaccinated, meaning 70% vaccination rate. So these are the statistics that we're gonna use. Now let us consider some probabilities. Actually, before we get to probabilities, we have to define some events. There are two important events that we need to consider. First, let V be the event that a person in this country is vaccinated. Then, the probability of event V is, that is, if we randomly pick a person in this country, the probability of that person being the vaccinated one is simply the vaccinated population divided by the entire population, which gives 7 over 10 or 0.7. Next, let H be the event that a person in this country is infected by the virus and thus hospitalized. Then, probability PH indicates the probability of picking a hospitalized person when we randomly pick a person from this country. This probability can be calculated by dividing the number of people hospitalized by entire population of the country, so 1,000 divided by 10 million, which gives 1 over 10,000 or 0.0001. Therefore, 0.01% of the total population is hospitalized with this disease. First, let us consider the dude's statement. 40% of all patients hospitalized for showing the symptoms of this disease are the ones who had already been vaccinated. Let us express this statement mathematically. The probability indicated in this statement is the conditional probability PV given H. The probability for event V to occur given that event H has already occurred. This can be calculated by the number of elements of V intersection H, the event of our interest, divided by the number of elements of H, which acts as a new sample space. That is, the number of people vaccinated and hospitalized divided by the number of people hospitalized, and from our data, we know that it is 400 divided by 1000, which gives the probability 2 over 5 or 0.4, just like the dude's claim. But like I said, this is not a suitable conditional probability to assess the effectiveness of vaccines. The probability that we really need is the conditional probability PH given V. That is, the probability of someone being hospitalized for the disease, given that person has been vaccinated. You can also use the number of elements like the previous one, but since this is an educational video about probabilities, let me show you how to calculate this conditional probability from other probabilities using the famous method probability of V intersection H divided by the probability of V. Here, we don't know the value of probability V intersection H, but if we also apply this formula to the previous conditional probability PV given H, we know that PV intersection H is given as PH times PV given H, where this probability PV given H is given as 40%. So PH is 1 over 10,000, PV given H is 2 over 5, and PV is 7 over 10, which gives the probability 1 over 17.5 thousand, or 0.0000571. This is 0.00571%, and it is a value clearly much lower than the aforementioned 40%, which is PV given H. Of course, we can calculate this probability directly from the given number of people, just like the previous one. It is now the number of people vaccinated among hospitalized divided by the number of people vaccinated, which is 400 divided by 7 million. Next, for the sake of comparison, let us calculate the probability of being hospitalized for this disease when not get vaccinated. This is the conditional probability PH given V complement. This can be calculated by PV complement intersection H divided by PV complement, where the numerator can be also written as PH times PV complement given H. Here, PH is 1 over 10,000, and PV complement given H is the probability of a person does not get vaccinated given that person is hospitalized. So it is 1 minus 2 over 5, the probability of a person is vaccinated given that person is hospitalized. And the probability of V complement is simply 1 minus probability of V, so 1 minus 7 over 10. This gives the result 1 over 5,000 or 0.0002, which in percentage is 0.02%. Of course, at this point, you may have realized that this probability can be also directly calculated from the number of people, where the numerator now becomes 600 people and the denominator now becomes 3 million people. Now that we have calculated the probabilities, let us compare them, consulting this table where the probabilities are summarized. Notice that aside from the first one, which is an incorrect probability to use, if we compare these two probabilities, you'll notice that the probability of getting the disease and being hospitalized when you are not vaccinated is approximately 3.5 times larger compared to when you are vaccinated. However, if we use incorrect probabilities for the argument, just like our dude, that is, if we use probabilities of a person being vaccinated or unvaccinated only under the given condition that such person is already hospitalized for the disease, we obtain much lower ratio of 1.5. This is one of the many examples demonstrating that when you are discussing probabilities related to disease occurrence rate, often combined with the effectiveness of vaccines or treatments, you must be cautious and use the correct conditional probabilities for your argument. And that's all for today's video. If you want to watch me calculating the probabilities related to the glass stepping stones game in the Netflix show Squid Game, please go check this video at the top, and please also go check other videos of my channel as well. Thank you all for watching, please don't forget to hit that like and subscribe buttons, and I will see you in another video.